The Andromeda Galaxy is not just big, it is a monster. Stretching across 220,000 light-years of space, this spiral giant contains 1 trillion stars, and right now, it is racing toward us at nearly 250,000 miles per hour. But here is what most people never realize. The galaxy you can see with your naked eye on a dark night, that faint smudge in the constellation Andromeda, is only a tiny fraction of the true structure. The visible part, all those trillion stars and swirling arms, makes up less than 1/5 of its actual size. The rest is invisible. It is a colossal halo of dark matter that extends for nearly 2 million light-years in every direction. And somewhere within that invisible ocean of matter, our own Milky Way galaxy is already beginning to interact with it. If you find topics like this fascinating, consider subscribing to the channel and hitting that like button. It helps us bring you more content about the incredible mysteries of our universe. To truly understand the scale of Andromeda, we need to step back and reconsider everything we think we know about galaxies. When we look at photographs of Andromeda, we see a beautiful spiral structure. We see bright arms filled with young blue stars. We see a glowing central bulge packed with older, redder stars. And this alone is impressive enough. But what we are really seeing is just the tip of an iceberg floating in an ocean we cannot see. The visible diameter of Andromeda, measuring from one edge of its stellar disk to the other, is about 220,000 light-years. To put that in perspective, if you could travel at the speed of light, the fastest speed possible in the universe, it would take you 220,000 years just to cross from one side to the other. That is more than 1,000 times longer than human civilization has existed. And yet, this visible disk, as enormous as it is, represents only a fraction of the galaxy's true extent. Surrounding this visible disk is something far larger and far more mysterious. It is called the galactic halo, and it is made primarily of dark matter. Scientists have discovered that this halo extends for roughly 1 million light-years from the center of Andromeda. In some measurements, it reaches even farther, stretching almost halfway to our own Milky Way galaxy. Think about what that means. Time, ones. The invisible part of Andromeda is so vast that it nearly touches our own galaxy's invisible halo. But what exactly is this dark matter halo? Why is it invisible? And how do we even know it exists if we cannot see it? These questions get to the heart of one of the biggest mysteries in modern astronomy. Dark matter is a substance that does not emit, absorb, or reflect light. It does not interact with ordinary matter in any way that we can directly detect. And yet, we know it exists because of the gravitational effects it has on everything around it. When astronomers first started measuring how far stars orbit around the centers of galaxies, they noticed something strange. The stars at the outer edges of galaxies were moving much faster than they should have been. According to the laws of physics, if a galaxy contained only the matter we could see, stars on the outskirts should orbit slowly, but instead, they orbit quickly, as if there is far more mass present than we can detect. This missing mass is what we call dark matter, and in Andromeda there is a lot of it. Current estimates suggest that the dark matter halo of Andromeda contains anywhere from 800 billion to over 1 trillion times the mass of our Sun. To appreciate how much mass that represents, consider that our entire Sun, a star so large that 1 million Earths could fit inside it, is just a single unit of measurement here. We are talking about 1 trillion of those, and most of this mass is spread out in an enormous sphere that dwarfs the visible galaxy, time ones. The discovery of Andromeda's dark matter halo actually played a key role in the history of astronomy. In 1970, astronomer Vera Rubin and her colleagues made groundbreaking observations of the gas clouds at the edge of Andromeda's disk. They found that these clouds were rotating far too fast to be held in place by the visible matter alone. This was one of the first pieces of solid evidence for the existence of dark matter, and it changed our understanding of the universe forever. Since then, astronomers have refined their measurements of Andromeda's mass many times. The most recent studies, published in 2025, actually suggest that Andromeda might be less massive than we previously thought. Using sophisticated computer models that account for a major collision, Andromeda experienced about 2.5 billion years ago. Researchers found that the galaxy's total mass might be around 450 billion solar masses. This is significantly less than earlier estimates, which place the mass at 2 to 4 times higher. However, even this revised figure represents an almost incomprehensible amount of matter. What makes these mass measurements so challenging is the fact that we are trying to weigh something we cannot see. Scientists use various techniques to estimate the dark matter content of Andromeda. One method involves studying the motions of satellite galaxies, the smaller galaxies that orbit around Andromeda. By measuring how fast these satellite galaxies move, astronomers can calculate how much gravity is pulling on them, and therefore how much mass must be present. Another technique involves looking at the rotation curve of Andromeda itself. The rotation curve is a graph showing how fast different parts of the galaxy are moving at different distances from the center. In a galaxy with no dark matter, the rotation speed would drop off at greater distances from the center, much like how outer planets in our solar system orbit more slowly than inner planets. But in Andromeda, and in most large galaxies, the rotation curve stays flat or even rises at large distances. This flat rotation curve is one of the strongest pieces of evidence for dark matter. The size of Andromeda's dark matter halo has important implications for what will happen when our two galaxies eventually meet. But before we explore that cosmic collision, let us first appreciate the scale of the visible galaxy itself, because even without considering the dark matter, Andromeda is truly enormous. At the center of Andromeda lies a supermassive black hole. This black hole contains the mass of roughly 100 million suns, compressed into a region smaller than our solar system. It is one of the largest black holes known in any nearby galaxy. And yet, compared to the galaxy surrounding it, this monster is almost insignificant. The supermassive black hole at the center of Andromeda represents less than 1% of the galaxy's total mass. Surrounding this black hole is the galactic bulge, a dense concentration of old red stars. The bulge of Andromeda is larger and more prominent than the bulge of our Milky Way. It contains about 30% of all the stars in the galaxy, tightly packed into a relatively small volume. If you were standing on a planet near the center of this bulge, the night sky would be blazingly bright, filled with so many stars that there would be no true darkness. Extending outward from the bulge is the galactic disk. This is where most of Andromeda's gas, dust, and young stars reside. The disk is arranged in beautiful spiral arms that wind outward from the center. These arms are not solid structures, but rather density waves, regions where matter tends to pile up. As gas clouds pass through these density waves, they get compressed, triggering the birth of new stars. This is why spiral arms often appear blue in photographs. They are filled with hot young stars that burn bright and fast. The disk of Andromeda is estimated to be about 220,000 light-years across. Some older measurements suggested it might be smaller, around 152,000 light-years, but more recent observations indicate the larger figure is more accurate. Either way, the disk is roughly twice the size of our Milky Way's disk, which spans about 100,000 light-years. Within this disk, there are approximately 1 trillion stars. This is about 2 to 3 times more stars than exist in our Milky Way. Each of these stars is a sun, a nuclear furnace converting hydrogen into helium and radiating energy into space. Many of these stars have planets orbiting them. Given the sheer number of stars in Andromeda, it is almost certain that billions of planets exist within this galaxy. Some of those planets may even harbor life. But stars are not the only things in Andromeda's disk. There is also a vast amount of gas and dust. The gas is primarily hydrogen, the simplest and most abundant element in the universe. Some of this hydrogen is in atomic form, floating as individual atoms through interstellar space. Other hydrogen is in molecular form, with 2 atoms bonded together. Molecular hydrogen is particularly important because it is the raw material from which new stars form. Andromeda contains at least 7.2 billion solar masses worth of neutral hydrogen gas. That is 7 billion times the mass of our Sun, just in hydrogen gas alone. On top of that, there is at least 340 million solar masses of molecular hydrogen in the inner regions of the galaxy. And scattered throughout the disk is about 54 million solar masses of interstellar dust. This dust may not sound like much compared to the gas, but it plays a crucial role in blocking and scattering starlight, creating the dark lanes we see in photographs of the galaxy. The stars in Andromeda are not all the same age. Like our own Milky Way, Andromeda has been forming stars for billions of years. The oldest stars are found in the galactic bulge and in the stellar halo, a sparse population of ancient stars that surrounds the disk. These old stars are typically red or orange in color, having long ago exhausted their supplies of hydrogen fuel. They are like dying embers, slowly fading over cosmic time. The youngest stars, in contrast, are found in the spiral arms of the disk. These are massive, hot blue stars that burn through their fuel quickly. A star like our Sun will shine for about 10 billion years, but a massive blue star might burn out in just a few million years. Despite their short lives, these massive stars are important because they produce heavy elements like carbon, oxygen, and iron in their cores. When they die in supernova explosions, they scatter these elements into space, enriching the gas from which future generations of stars and planets will form. Andromeda also has a population of globular clusters. These are dense, spherical collections of stars that orbit around the galaxy. Unlike the open clusters found in the disk, which contain a few hundred to a few thousand stars, globular clusters can contain hundreds of thousands or even millions of stars packed into a relatively small volume. Andromeda has more than 400 known globular clusters, far more than the roughly 150 known in our Milky Way. One of Andromeda's globular clusters deserves special mention. It is called Maiol 2, and it is the most luminous globular cluster in the entire local group of galaxies. Maiol 2 contains millions of stars and is so bright that it can be observed with amateur telescopes despite being over 2 million light-years away. Some astronomers believe that Maiol 2 might actually be the remnant core of a dwarf galaxy that was absorbed by Andromeda long ago. Speaking of the local group, this brings us to a crucial aspect of understanding Andromeda's scale. Andromeda is not alone in space. It is part of a family of galaxies known as the local group, which includes our Milky Way the Triangulum Galaxy, and dozens of smaller dwarf galaxies. The local group spans about 10 million light-years and contains more than 80 known galaxies. Within this family, Andromeda is the largest member. It is the dominant galaxy, the gravitational center around which many smaller galaxies orbit. Andromeda has at least 25 satellite galaxies of its own, including the famous M32 and M110, which can be seen in photographs as small fuzzy patches near the main galaxy. These satellite galaxies are slowly being torn apart and absorbed by Andromeda's immense gravity. In fact, evidence suggests that Andromeda has cannibalized hundreds of smaller galaxies over its lifetime, growing larger with each cosmic meal. The distance between Andromeda and our Milky Way is approximately 2.5 million light-years. This means that when you look at Andromeda tonight, the light entering your eyes left that galaxy 2.5 million years ago. You are seeing Andromeda as it appeared when early human ancestors were just beginning to walk upright on the plains of Africa. Light from Andromeda has been traveling through the void of space for longer than our species has existed. 2.5 million light-years is an almost impossible distance to comprehend. Light travels at 186,000 miles per second. In 1 year, light covers about 6 trillion miles. Multiply that by 2.5 million, and you get a distance so vast that no analogy can truly capture it. If you could drive a car at highway speed to Andromeda, it would take you over 30 trillion years to arrive. That is more than 2,000 times longer than the current age of the universe. And yet, despite this incredible distance, Andromeda and the Milky Way are not drifting apart. They are moving toward each other. The Andromeda Galaxy is approaching us at a speed of about 110 kilometers per second, which translates to roughly 250,000 miles per hour. This might sound fast, and it is by human standards, but compared to the distances involved, it is almost imperceptibly slow. At this rate, it will take billions of years for the two galaxies to meet, but the encounter is coming, and when it happens, it will transform both galaxies forever. The question of exactly when and how this collision will occur has been debated by astronomers for over a century. But recent observations have finally given us a clearer picture of what the future holds. In 2012, astronomers used the Hubble Space Telescope to make precise measurements of how Andromeda is moving across the sky. By comparing images taken in 2002 and 2010, they could detect tiny shifts in the positions of stars in Andromeda relative to background galaxies. This allowed them to determine not just how fast Andromeda is approaching us, but also how fast it is moving sideways. The results were dramatic. The sideways motion of Andromeda turned out to be very small, essentially consistent with zero. This meant that Andromeda was heading almost directly toward us. A collision was not just possible, but almost certain. The researchers announced that the two galaxies would merge in approximately 4 billion years. However, the story has become more complicated in recent years. In 2025, a new study using data from both the Hubble Space Telescope and the Gaia spacecraft challenged this conclusion. By accounting for the gravitational influence of other nearby galaxies, particularly the Large Magellanic Cloud and the Triangulum Galaxy, the researchers found that the future was less certain than previously thought. According to this newer analysis, there is only about a 50% chance that the Milky Way and Andromeda will collide within the next 10 billion years. The Large Magellanic Cloud, a satellite galaxy of the Milky Way, exerts a gravitational tug that could pull our galaxy slightly off course. Meanwhile, the Triangulum Galaxy pulls Andromeda in a different direction. These competing influences create uncertainty about the exact trajectories of both galaxies. Even so, the most likely scenario remains some kind of close encounter between the two giants. Whether it is a direct head-on collision or a close flyby that eventually leads to a merger, the fate of both galaxies is intertwined. And when we consider the timescales involved, a few billion years is not really that long in cosmic terms. Let us pause for a moment and consider what this collision would actually look like. When we hear the word collision, we imagine a violent crash, with objects smashing into each other and being destroyed. But a galactic collision is nothing like that. Galaxies are mostly empty space. Even within the densest parts of a galaxy, the distances between individual stars are enormous. Consider our own solar neighborhood. The nearest star to our Sun is Proxima Centauri, about 4.2 light-years away. If the Sun were the size of a ping-pong ball, Proxima Centauri would be another ping-pong ball, located about 680 miles away. Now imagine trying to crash two clouds of ping-pong balls together when the balls are separated by hundreds of miles. The chances of any two balls actually hitting each other are essentially zero. This is what a galactic collision is like. When Andromeda and the Milky Way merge, it is extremely unlikely that any two stars will directly collide. Instead, what happens is a gravitational dance. The galaxies pass through each other like ghosts, but their gravity pulls and tugs on everything, distorting the shapes of both galaxies and flinging stars into new orbits. Computer simulations show what this process might look like. About 2 billion years from now, Andromeda will start to appear noticeably larger in Earth's night sky, assuming Earth still exists and has a clear atmosphere. By 3.75 billion years, Andromeda will fill a significant portion of the sky, appearing much larger than the full moon does today. Around 4 billion years from now, the first close encounter will occur. The two galaxies will sweep past each other, their spiral arms becoming distorted and stretched. New stars will form in vast numbers as gas clouds collide and compress. The night sky, if anyone were there to see it, would be ablaze with the light of stellar nurseries. The galaxies will then swing apart, only to fall back toward each other under the influence of their mutual gravity. This cosmic dance will repeat, with each pass stripping more stars and gas from the original structures. Eventually, after about 7 billion years, the two galaxies will fully merge into a single, massive elliptical galaxy. Astronomers have nicknamed this future galaxy Milkomeda, a combination of Milky Way and Andromeda. The merged galaxy will be very different from either of its parent galaxies. Spiral structure will be destroyed. The beautiful arms that currently define both Andromeda and the Milky Way will be gone, replaced by a more amorphous blob of stars. The central supermassive black holes of both galaxies will eventually find each other and merge, creating an even more massive black hole at the center of Milkomeda. What about our solar system? Where will Earth end up in this cosmic reshuffle? Simulations suggest that our solar system will probably be flung outward from the galactic center, ending up much farther from the core of the new galaxy than we are from the center of the Milky Way today. There is also a small chance, about 12%, that the solar system could be ejected entirely from the merged galaxy, sent off to drift through intergalactic space. Of course, by the time any of this happens, Earth will no longer be habitable. The Sun is gradually growing hotter as it ages, and in about 1 billion years, Earth's oceans will evaporate and the planet will become too hot for life. Long before Andromeda arrives, our descendants, if they still exist, will need to have found a new home somewhere else. The collision with Andromeda is the least of our cosmic worries, but the collision itself is not really the point of this story. The point is to understand the incredible scale of what we are dealing with. Andromeda is not just a distant smudge in the sky. It is a colossal structure, larger than almost anything else in our cosmic neighborhood. Its dark matter halo extends for millions of light years. Its trillion stars represent a city of suns, each one potentially hosting its own family of planets. And this giant is connected to us, bound by gravity, destined to become part of our own galaxy's future. To fully appreciate Andromeda's scale, we need to zoom out even further and consider where it fits in the larger structure of the universe. The local group, containing both Andromeda and the Milky Way, is itself just a small part of a much larger structure called the Virgo supercluster. The Virgo supercluster is a collection of galaxy groups and clusters spanning about 110 million light years. At its heart lies the Virgo cluster, a massive aggregation of more than 2,000 galaxies located about 65 million light years from Earth. The local group sits at the outer edge of this supercluster, like a small town on the outskirts of a major metropolitan area. But even the Virgo supercluster is not the largest structure we belong to. In 2014, astronomers discovered that the Virgo supercluster is itself just a small part of an even larger structure called Laniakea. The name comes from Hawaiian and means immense heaven. Laniakea contains about 100,000 galaxies and spans 520 million light years. It is centered on a region called the Great Attractor, a gravitational anomaly that is pulling galaxies toward it from all directions. Within this hierarchy of structures, Andromeda occupies a unique position. It is the largest galaxy in the local group, but the local group is small compared to the Virgo cluster. The Virgo cluster is significant within the Virgo supercluster, but the supercluster is just one small piece of Laniakea, and Laniakea is just one of millions of such structures in the observable universe. So how does Andromeda compare to the truly massive galaxies out there? In the grand scheme of things, Andromeda is a large spiral galaxy, but not exceptionally so. There are elliptical galaxies that dwarf Andromeda many times over. The giant elliptical galaxy M87, located at the center of the Virgo cluster, contains several trillion stars and is surrounded by thousands of globular clusters. It has a supermassive black hole over 6 billion times the mass of the Sun, far larger than Andromeda's central black hole. Even larger galaxies exist. IC 1101, one of the largest known galaxies, is a supergiant elliptical that may contain as many as 100 trillion stars. Its diameter is estimated at about 6 million light years, making it roughly 30 times larger than Andromeda. Compared to monsters like this, Andromeda is almost modest. But Andromeda is special for a different reason. It is ours. It is the largest galaxy in our immediate cosmic neighborhood, the dominant member of our local group, and the most distant object that can be seen with the naked eye. When you look up at the night sky and spot that faint fuzzy patch in the constellation Andromeda, you are seeing light that has traveled for 2.5 million years to reach you. You are looking back in time to an era before modern humans existed, and you are seeing a galaxy that, in the distant future, will become part of our own. The scale of Andromeda challenges our imagination in ways that few other objects can. It is large enough to contain 1 trillion suns, yet it appears as just a tiny smudge in our sky. Its dark matter halo extends for millions of light years, yet we cannot see it at all. It is rushing toward us at incredible speed, yet it will take billions of years to arrive. Every aspect of Andromeda forces us to reconsider our place in the cosmos and to confront the almost unfathomable vastness of the universe we inhabit. The methods astronomers use to measure Andromeda's distance deserve special attention, because understanding how we know the distance helps us appreciate how remarkable that knowledge truly is. For most of human history, we did not even know that Andromeda was a galaxy. It was classified as a nebula, a fuzzy cloud thought to exist within our own Milky Way. The idea that there might be other galaxies beyond our own was considered by some thinkers throughout history, but there was no way to prove it. The breakthrough came in the early 20th century, thanks to a type of star called a Cepheid variable. Cepheid variables are pulsating stars that regularly brighten and dim over periods ranging from days to months. In 1912, astronomer Henrietta Swan Leavitt discovered that there is a precise relationship between a Cepheid's pulsation period and its intrinsic brightness. A Cepheid that pulsates slowly is genuinely brighter than one that pulsates quickly. This discovery was revolutionary because it provided a cosmic measuring tape. If you can measure how long a Cepheid takes to complete one pulse, you know how bright it truly is. Then, by measuring how bright it appears to be from Earth, you can calculate how far away it must be. The difference between actual brightness and apparent brightness tells you the distance. In 1923 and 1924, astronomer Edwin Hubble used the 100-inch telescope at Mount Wilson Observatory to observe Andromeda. He found Cepheid variable stars within the nebula and calculated their distances using Leavitt's method. The results were astonishing. Andromeda was not a nearby cloud of gas. It was a vast collection of stars located far beyond the boundaries of our own galaxy. The universe, it turned out, was much larger than anyone had imagined. Hubble's initial distance estimate placed Andromeda at about 900,000 light-years away. This was later revised upward as astronomers refined their understanding of Cepheid variables. The current best estimate, based on decades of observations with ground-based and space-based telescopes, places Andromeda at approximately 2.5 million light-years from Earth. The precision of modern measurements is remarkable. We can now pinpoint Andromeda's distance to within about 5% accuracy. But distance is just one aspect of the scale problem. Understanding the true extent of Andromeda, its diameter, and the reach of its dark matter halo requires entirely different techniques. For the visible galaxy, astronomers use a standard called the D25 isophote. This is the contour where the surface brightness of the galaxy falls to a certain level. Think of it like drawing a line around a glowing object where the glow reaches a specific faintness. Using this method, Andromeda's stellar disk measures about 152,000 light-years across, according to some studies, or about 220,000 light-years according to others. The difference in these measurements comes from where you draw the line. The outer edges of a galaxy are fuzzy, not sharp. Stars become increasingly sparse as you move away from the center. There is no clear boundary where the galaxy ends and empty space begins. Instead, the density of stars gradually fades until individual stars are separated by vast distances. Depending on how you define the edge, you get different diameter estimates. The dark matter halo presents an even greater challenge. Since dark matter does not emit light, we cannot photograph it directly. Instead, we must infer its presence from gravitational effects. One powerful technique involves studying the motion of satellite galaxies. Andromeda has at least 25 known satellite galaxies, small galaxies that orbit around the main body. By measuring how fast these satellites are moving, and at what distances, astronomers can calculate how much mass must be pulling on them gravitationally. Another technique uses gravitational lensing. When light from a distant background galaxy passes near Andromeda, the gravity of Andromeda's dark matter bends that light slightly. By studying how the images of background galaxies are distorted, astronomers can map where the dark matter is concentrated and how far it extends. These studies suggest that Andromeda's dark matter halo reaches roughly 1 million light-years from the galaxy's center, perhaps even farther in some directions. A fascinating study published in 2020 used the Hubble Space Telescope to probe Andromeda's halo using a different method. Researchers looked at distant quasars, extremely bright objects powered by supermassive black holes that lie behind Andromeda. As light from these quasars passes through Andromeda's halo, it gets absorbed by gas that exists within the halo. By analyzing which wavelengths of light are absorbed, astronomers can determine what kind of gas is present and how much of it there is. The results revealed that Andromeda is surrounded by an enormous envelope of hot gas. This gaseous halo extends at least 1 million light-years from the galaxy's center and contains roughly half as much mass as all the stars in the visible galaxy. The gas is extremely diffuse, with only about 1 atom per cubic foot on average. But spread over such an immense volume, it adds up to a staggering amount of material. This gaseous halo is constantly being enriched by supernovae within Andromeda's disk. When massive stars explode, they eject heavy elements like oxygen, carbon, and iron into space at tremendous velocities. Some of this material ends up falling back into the galaxy, recycling into new generations of stars and planets. But much of it gets blown completely out of the disk and ends up in the surrounding halo. Over billions of years, roughly half of all the heavy elements produced by Andromeda's stars have ended up in this vast gaseous envelope. The interaction between the gaseous halos of Andromeda and the Milky Way is particularly intriguing. Our own galaxy is also surrounded by a hot gas halo, though it may not be quite as extensive as Andromeda's. Some astronomers believe that these two halos are already beginning to touch. If true, this would mean that the merger between our galaxies has, in some sense, already begun. The visible galaxies themselves are still separated by more than 2 million light-years, but their invisible envelopes are brushing against each other like the fingers of 2 hands slowly reaching out to clasp. The stars within Andromeda's halo tell their own story of the galaxy's violent past. Unlike the orderly orbits of stars in the disk, halo stars move in chaotic, randomly oriented orbits. Many of these stars are ancient, among the oldest in the entire galaxy. But there are also streams of stars that follow coherent paths through the halo, like rivers of light flowing through the darkness. The most famous of these is the giant stellar stream, a long ribbon of stars that wraps around Andromeda. This stream is thought to be the remains of a small galaxy that was torn apart by Andromeda's gravity long ago. As the doomed galaxy fell inward, tidal forces stretched it out like taffy, leaving a trail of stars behind. The giant stellar stream is visible in deep photographs and provides direct evidence that Andromeda has been devouring smaller galaxies for billions of years. Modeling of this stream and other structures in Andromeda's halo has led astronomers to conclude that Andromeda experienced a major collision about 2 to 3 billion years ago. This was not a minor merger with a small dwarf galaxy, but a significant event involving a galaxy perhaps 1/4 the mass of Andromeda itself. The collision would have triggered intense bursts of star formation, transformed the structure of Andromeda's disk, and created many of the features we observe today. the central bar of Andromeda, a dense, elongated structure at the galaxy's core, may have formed as a result of this collision. Bars are common in spiral galaxies, including our own Milky Way, but Andromeda's bar has some unusual properties that suggest it was created or enhanced by a galactic interaction. The bar spans about 27,000 light-years in length and 6,000 light-years in width, making it a significant feature despite being dwarfed by the overall galaxy. Understanding Andromeda's structure helps us understand spiral galaxies in general. As the nearest large spiral to our own, Andromeda serves as a laboratory for studying galactic processes. We can observe individual stars, map the distribution of gas and dust, and watch for transient events like novae and supernovae. In many ways, studying Andromeda helps us understand our own Milky Way, since we cannot observe our own galaxy from the outside. This brings us to an important point about perspective. We are embedded within the Milky Way, surrounded by its stars and gas. This makes it extremely difficult to understand our own galaxy structure. It is like trying to understand the layout of a forest while standing among the trees. But Andromeda offers us an external view of a galaxy similar to our own. By studying Andromeda, we gain insights into what the Milky Way might look like from far away. And yet, there are significant differences between the two galaxies. Andromeda appears to be older than the Milky Way, with a more prominent bulge and lower current star formation rate. The Milky Way produces new stars at a rate of about 1 to 3 solar masses per year. Andromeda produces new stars at only about half that rate, around half to 1 solar mass per year. This suggests that Andromeda may be in a later stage of its galactic evolution. The difference in star formation rates may be connected to the amount of cold gas available. Star formation requires dense clouds of molecular hydrogen, and galaxies that have used up or expelled most of their gas will naturally form fewer new stars. Andromeda's lower star formation rate suggests that it may have less raw material available for making new stars than the Milky Way does. Interestingly, the collision that Andromeda experienced 2 to 3 billion years ago probably triggered an intense burst of star formation at the time. During such mergers, gas clouds that would normally remain stable can be compressed and destabilized, collapsing to form new stars in great numbers. Some astronomers estimate that during the peak of this interaction, Andromeda may have been forming stars at 10 times or more its current rate. It would have been a luminous infrared galaxy, glowing brilliantly with the light of countless stellar nurseries. That period of intense activity has long since passed. The gas has settled back down, the starburst has faded, and Andromeda has returned to a more quiescent state. But the evidence of that violent era remains imprinted in the galaxy's structure, in the streams of stars in its halo, in the patterns of stellar ages across its disk, and in the unusual properties of its central regions. The satellite galaxies of Andromeda provide additional clues about its history and structure. The two most prominent satellites are M32 and M110, both of which are visible in amateur telescopes as small fuzzy spots near the main galaxy. M32 is a compact elliptical galaxy, unusually dense for its size. M110 is a more typical dwarf elliptical, larger but less concentrated. M32 in particular has puzzled astronomers. It is abnormally compact, with stars packed far more densely than in other galaxies of similar mass. One theory suggests that M32 was once much larger, perhaps a substantial spiral galaxy in its own right. As it orbited Andromeda, tidal forces stripped away its outer layers, leaving only the dense core behind. If true, This would mean that M32 is actually the corpse of a once great galaxy, reduced to a fraction of its former size by Andromeda's gravitational appetite. Simulations support this idea. When a smaller galaxy passes close to a larger one, the gravity of the larger galaxy stretches and distorts the smaller one. Stars on the side closest to the larger galaxy feel a stronger pull than stars on the far side. This differential pull, called tidal force, can strip away the outer regions of the smaller galaxy over time. What remains is the dense core, resistant to further tidal stripping because its gravity holds it together more tightly. The 25 or so known satellite galaxies of Andromeda range from relatively substantial objects like M32 and M110 down to tiny dwarf spheroidal galaxies containing only a few million stars. These dwarf galaxies are the most dark matter-dominated objects in the universe. Their stars are so sparse that visible matter makes up only a tiny fraction of their total mass. The rest is dark matter, holding the dwarf galaxies together despite their apparently meager stellar populations. Studying these satellite galaxies helps astronomers understand dark matter on small scales. The properties of dwarf galaxies, such as their internal velocities and density profiles, provide constraints on the nature of dark matter particles. If dark matter is cold and slow-moving, as most models predict, we would expect certain patterns in the structure of dwarf galaxies. If dark matter is warm and faster moving, the patterns would be different. By comparing observations with predictions, astronomers can test different dark matter theories. The distribution of satellite galaxies around Andromeda also raises interesting questions. Many of Andromeda's satellites appear to orbit in a thin plane, rather than being randomly scattered around the galaxy. This planar arrangement was initially surprising, since simple models of galaxy formation predict a more spherical distribution. Similar planar arrangements have been found around the Milky Way, leading some astronomers to question whether our understanding of galaxy formation is missing something important. Various explanations have been proposed for these planar satellite distributions. One possibility is that the satellites were accreted from a particular direction, perhaps falling in along a cosmic filament of matter. Another possibility is that some of the satellites formed together from material stripped during a past galactic interaction. The debate continues, with new observations of satellite galaxy motions helping to constrain the possibilities. Moving beyond the satellites, let us consider the space between Andromeda and the Milky Way. This region, spanning more than 2 million light-years, is not completely empty. The local group contains numerous small galaxies scattered throughout this volume. Some are satellites of the Milky Way, others are satellites of Andromeda, and some are field galaxies, not clearly bound to either of the two giants. The Triangulum Galaxy, also known as M33, is the third largest member of the local group. With about 40 billion stars, it is significantly smaller than either Andromeda or the Milky Way, but still substantial enough to be visible with the naked eye under excellent conditions. Triangulum lies about 2.7 million light-years from Earth, slightly more distant than Andromeda, but in approximately the same direction on the sky. Triangulum appears to be gravitationally bound to Andromeda, though the exact nature of their relationship is still being investigated. Some simulations suggest that Triangulum has already completed one close pass of Andromeda in the past, with the encounter distorting its spiral structure. The two galaxies may merge in the distant future, or Triangulum may be captured and absorbed during the Andromeda-Milky Way collision. The fate of Triangulum is yet another variable in the complex equation of local group evolution. When modeling the future of our cosmic neighborhood, astronomers must account for the gravity of Andromeda, the Milky Way, Triangulum, the Large Magellanic Cloud, and dozens of smaller galaxies. Each of these objects pulls on every other object, creating a gravitational web of interactions that is difficult to calculate precisely. The Large Magellanic Cloud deserves special mention here. This satellite galaxy of the Milky Way is one of the most massive satellite galaxies known, containing about 10 billion stars. Its gravity significantly affects the motion of the Milky Way itself. Recent studies have shown that the Large Magellanic Cloud is pulling the Milky Way off course, changing our trajectory through space. This tug may actually reduce the probability of a direct collision with Andromeda, as I mentioned earlier. The interplay between all these gravitational influences creates considerable uncertainty about the future. While the general outline seems clear, with Andromeda and the Milky Way approaching each other and likely merging within the next 10 billion years, the details remain fuzzy. Will it be a direct collision or a glancing encounter? Will Triangulum join the merger or escape into intergalactic space? Will the merged galaxy be a giant elliptical or something more unusual like a huge lenticular galaxy? These questions cannot be answered with certainty based on current observations. What we can say with confidence is that the scale of this future interaction will be enormous. Two galaxies, each containing hundreds of billions or trillions of stars, each surrounded by halos of dark matter extending for millions of light years, will dance around each other, pass through each other, and eventually combine into a single vast structure. The gravitational forces involved are beyond human comprehension. The timescales involved are beyond human experience, and the result will be a transformation of our cosmic neighborhood that will endure for billions of years to come. The comparison between Andromeda and other cosmic structures helps put all of this in perspective. We have already discussed the local group, the Virgo supercluster, and the Laniakea supercluster. But let us take a moment to appreciate the numbers involved. The local group spans about 10 million light years. Andromeda's dark matter halo extends for about 1 to 2 million light years. So Andromeda alone fills a significant fraction of the space within the local group. When you add in the Milky Way's halo, which extends perhaps 1 million light years from our galactic center, the two giants and their halos occupy much of the local group's volume. The smaller galaxies exist in the spaces between and around these two dominant structures. The Virgo supercluster is about 10 times larger than the local group, spanning roughly 110 million light years. Within this volume, there are at least 100 galaxy groups and clusters, including the Virgo cluster itself, with over 2,000 member galaxies. The local group is just one of these 100 groups, and not particularly prominent among them. We are located at the outer edge of the supercluster, far from the dense concentrations of galaxies at its center. Laniakea is larger still, spanning over 500 million light years and containing an estimated 100,000 galaxies. The Virgo supercluster is just one small part of this immense structure, and Laniakea itself is just one of millions of similar structures in the observable universe. So where does Andromeda fit in this cosmic hierarchy? At the scale of the local group, Andromeda is the dominant object, the largest and most massive galaxy in the neighborhood. At the scale of the Virgo supercluster, Andromeda is just another moderately large spiral galaxy, one among hundreds. At the scale of the observable universe, Andromeda is a single grain of sand on a vast beach. And yet, for us, Andromeda is special. It is our nearest large galactic neighbor. It is the most distant object we can see with our unaided eyes. It is the galaxy that will someday merge with our own. Among all the billions of galaxies in the universe, Andromeda is the one that matters most to our cosmic future. The velocity at which Andromeda approaches us tells its own story about cosmic scale. 110 kilometers per second sounds fast. It is more than 250,000 miles per hour. A spacecraft traveling at this speed could reach the moon in less than an hour and could cross the diameter of Earth's orbit in about a week. But space is vast, and the distance to Andromeda is so great that even this tremendous velocity covers only a tiny fraction of the gap each year. Let us do the math. At 110 kilometers per second, Andromeda moves about 3.5 billion kilometers closer to us every year. That sounds like a lot, but 3.5 billion kilometers is only about 23 times the distance from Earth to the Sun. Meanwhile, the total distance to Andromeda is about 2.5 million light years, which is roughly 24 trillion kilometers. At this rate, it would take Andromeda nearly 7 billion years to reach us, though the actual time is shorter because the galaxies accelerate as they approach. The acceleration happens because gravity strengthens as the galaxies get closer. When two massive objects are far apart, the gravitational force between them is relatively weak. As they approach, the force increases, pulling them together faster and faster. This means the approach velocity of Andromeda is not constant. It is increasing, slowly but steadily, as the eons pass. There is something poetic about this cosmic approach. Two islands of stars, each home to trillions of worlds, drifting toward each other across the void. Their meeting is inevitable, yet so far in the future that countless generations of stars will be born and die before it happens. The timescale is truly astronomical, measured not in human lifetimes or even civilizational lifetimes, but in the lifetimes of stars. Consider what will happen in the billions of years before the collision. Our Sun will exhaust its hydrogen fuel in about 5 billion years, swelling into a red giant that will consume or scorch the inner planets. Long before Andromeda arrives, Earth will be a lifeless cinder, its oceans boiled away, its atmosphere stripped by solar radiation. Any descendants of humanity who wish to witness the collision will need to have relocated to safer havens, perhaps to worlds orbiting younger stars in the outer reaches of the galaxy. Even as our Sun ages, new stars will be born in both galaxies. Clouds of gas will collapse, ignite and shine. Planets will form from the debris orbiting these new stars. On some of those planets, life might arise, perhaps intelligent life that will one day look up at its sky and wonder about the strange fuzzy patch growing ever larger over the generations. When the collision finally comes, it will happen in slow motion by human standards. Galaxies are so large that even at closing speeds of hundreds of kilometers per second, the merger process takes hundreds of millions of years. The inhabitants of any civilization still existing in either galaxy would have plenty of time to observe, document, and perhaps even relocate if necessary. The first dramatic changes would be visible about 2 billion years before closest approach. The Andromeda Galaxy, which today appears as a faint smudge about 3 degrees across, would begin to grow noticeably larger. Its spiral arms would become visible to the naked eye on dark nights. Two distant island universes, long aware of each other's existence, would finally seem to be reaching out to touch. About 3.75 billion years from now, the galaxies would be close enough that Andromeda would fill a large portion of the night sky. Looking up from any planet in either galaxy, observers would see the other galaxy stretching across the heavens, its spiral arms visible in glorious detail. The gravitational interaction between the galaxies would already be causing subtle distortions, warping the outer edges of both spiral structures. At 3.85 billion years, the sky would begin to blaze with new star formation. As the two galaxies approached their first close passage, gas clouds that had been stable for billions of years would be compressed and destabilized. These clouds would collapse rapidly, giving birth to swarms of new stars. The night sky of any observers would be filled with bright blue stellar nurseries, emission nebulae glowing red and pink, and young star clusters sparkling like jewels scattered across the cosmic canvas. The first close passage, around 4 billion years from now, would be a spectacular but not catastrophic event. The galaxies would sweep past each other, their centers perhaps passing within a few 100,000 light years. Tidal forces would stretch and distort both galaxies dramatically. The beautiful spiral arms that define both Andromeda and the Milky Way would begin to unravel, pulled outward into long tidal tails of stars. During this first passage, individual stars would experience changes in their orbits. Some stars would be accelerated to higher velocities, gaining energy from the gravitational interaction. Others would be slowed down. A few unlucky stars might be flung out of the galaxies entirely, sent spinning off into the void of intergalactic space. But the vast majority of stars would remain gravitationally bound, carried along with the flow of the merger. After the first passage, the galaxies would continue moving apart, carried by their momentum. But gravity is persistent. The mutual attraction between the two massive systems would slow their separation, stop them, and then pull them back together. The second approach would happen after another few 100 million years. With each successive pass, the galaxies would lose more orbital energy. This energy does not disappear. It is redistributed, transferred from the large-scale motion of the galaxies to the smaller-scale motions of individual stars. Stars gain random velocities as the gravitational field fluctuates during the merger. This process, called dynamical friction, gradually saps the energy from the orbital motion of the two galaxies. After several passes over the course of 1 to 2 billion years, the two galaxies would finally coalesce. The distinct spiral structures would be destroyed, replaced by a single massive blob of stars. The resulting galaxy would be an elliptical or lenticular shape, without the flat disk and spiral arms that characterize the original galaxies. At the center of this new galaxy, the two supermassive black holes, one from Andromeda and one from the Milky Way, would begin their own merger dance. Initially separated by thousands of light years, the black holes would sink toward the center of the combined galaxy, drawn there by dynamical friction. As they approached each other, they would form a binary system, orbiting each other at ever-decreasing distances. The final merger of the two black holes would happen when they were close enough for gravitational radiation to drain their orbital energy. Gravitational waves, ripples in spacetime, predicted by Einstein's general relativity and directly detected for the first time in 2015, would carry energy away from the system. The black holes would spiral inward faster and faster until they finally collided and merged in a cataclysmic event. This black hole merger would release an enormous amount of energy in the form of gravitational waves. For a brief instant, the power output in gravitational radiation would exceed the light output of all the stars in the observable universe. But gravitational waves interact only weakly with matter, so this burst of energy would pass through the universe essentially unnoticed, except by extremely sensitive detectors. The merged black hole would settle down to a new equilibrium state. It would be more massive than either of the original black holes, containing perhaps 200 million solar masses or more. Surrounding it would be a vast, elliptical galaxy containing well over 1 trillion stars. This new galaxy, Milkomeda, would be one of the largest galaxies in the local group, though by the time it forms, the local group as we know it will have been transformed beyond recognition. But let us return to the present day and consider what the scale of Andromeda tells us about the universe in general. Galaxies like Andromeda are the building blocks of cosmic structure. They are the largest gravitationally bound objects in the universe. Superclusters and larger structures are not gravitationally bound in the same way. They are expanding with the universe, gradually pulling apart over cosmic time. But galaxies and the dark matter, halos that surround them, are held together by their own gravity. The existence of galaxies with trillion star populations and dark matter halos extending for millions of light years tells us something fundamental about the history of the universe. These structures did not form overnight. They grew slowly over billions of years, accreting gas, forming stars, and emerging with other galaxies. The Andromeda we see today is the product of nearly 14 billion years of cosmic evolution. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly. There were no galaxies, no stars, just a hot, dense plasma of fundamental particles. But tiny variations in density, quantum fluctuations amplified during cosmic inflation, provided the seeds for structure formation. Regions that were slightly denser than average had slightly stronger gravity, which pulled in more matter from surrounding regions, making them even denser. Over hundreds of millions of years, these small overdensities grew into the first halos of dark matter. Within these halos, ordinary matter, mostly hydrogen and helium gas, began to collect. The gas cooled and condensed, eventually reaching densities high enough for stars to form. The first stars were probably quite different from stars today. Massive and short-lived, formed from pristine gas with no heavy elements. These early stars lived fast and died young, exploding as supernovae and enriching the surrounding gas with the first heavy elements. Carbon, oxygen, iron, and the other elements necessary for planets and life were forged in the hearts of these stellar furnaces and scattered into space by their violent deaths. Subsequent generations of stars formed from gas enriched with these heavy elements. Planets could now form around these stars, built from the rocky and metallic debris left over from star formation. On at least one of those planets, Earth, the conditions were right for life to arise, but that is getting ahead of ourselves. As the universe aged, small galaxies merged to form larger ones. The hierarchical structure formation model, as cosmologists call it, describes a universe where small things come first and big things are built from the merger of smaller components. Andromeda itself is the product of countless mergers over cosmic time. It has absorbed hundreds of smaller galaxies, growing larger with each acquisition. Evidence of these past mergers is written in the structure of Andromeda today. The streams of stars in its halo are the remnants of digested galaxies. The unusual properties of its central regions may reflect the aftermath of a major collision. Even the satellite galaxies currently orbiting Andromeda will eventually be consumed, their stars incorporated into the ever-growing giant. Our Milky Way has a similar history. We too have grown by devouring smaller neighbors. The Sagittarius dwarf galaxy is currently being torn apart and absorbed by our galaxy. Other streams of stars in our halo testify to galaxies that were consumed long ago. We are not innocent observers of cosmic cannibalism. We are participants, both predator and eventually prey. The scale of these processes is difficult to appreciate. A single galaxy merger might take 1 billion years to complete. During that time, billions of stars are born and die. Civilizations might rise and fall. The merger itself is imperceptible on human timescales, happening so slowly that no single observer could possibly notice the change. And yet, over cosmic time, these mergers fundamentally reshape the universe, building larger and larger structures from smaller components. Andromeda represents a snapshot of this process, frozen in a moment of cosmic time. When we observe Andromeda, we are seeing a galaxy that has already completed many mergers and is preparing for its next and perhaps most significant one. The merger with the Milky Way will be the defining event in the future history of both galaxies, transforming two distinct spiral structures into a single giant elliptical. The velocity measurements that reveal Andromeda's approach are themselves a testament to human ingenuity. When we look at Andromeda, the light we receive is shifted slightly toward the blue end of the spectrum. This blue shift is caused by the Doppler effect, the same phenomenon that makes an approaching ambulance siren sound higher pitched than a receding one. Light from an approaching object gets compressed, shifting its color toward the blue. By measuring the precise amount of blue shift in Andromeda's light, astronomers can determine how fast the galaxy is approaching us. But this only tells us the radial velocity, the component of motion directly toward or away from us. To determine whether Andromeda will actually hit us or pass by, astronomers also needed to measure the transverse velocity, the component of motion across the sky. Measuring transverse velocity is much harder than measuring radial velocity. The motion across the sky is called proper motion, and for distant objects like galaxies, it is incredibly small. Andromeda is so far away that even moving at over 100 kilometers per second across the sky, its position shifts by only a tiny fraction of a degree over human lifetimes. Detecting this shift requires extremely precise measurements taken over years or decades. The breakthrough came from observations made with the Hubble Space Telescope. By photographing the Earth's same stars in Andromeda over a span of years and comparing their positions relative to distant background galaxies, astronomers could detect the minuscule shift in Andromeda's position. The results, published in 2012, showed that Andromeda's transverse velocity is very small, essentially zero within the measurement uncertainties. This meant Andromeda was heading almost directly toward us. More recent observations with the Gaia spacecraft have refined these measurements further. Gaia is a European Space Agency mission designed to measure the positions and motions of billions of stars with unprecedented precision. By observing stars in Andromeda and its satellite galaxies, Gaia has helped astronomers better understand the three-dimensional motion of our neighbor galaxy. The combination of Hubble and Gaia data, together with sophisticated computer simulations, has given us the current picture of Andromeda's future trajectory. While uncertainties remain, we can now say with reasonable confidence that some kind of close encounter or merger is likely within the next 10 billion years. The exact timing and nature of that encounter depends on factors we cannot yet measure precisely, including the total masses of both galaxies and the gravitational influence of other nearby objects. This uncertainty itself is instructive. Despite centuries of observations and the most advanced technology ever created, we cannot predict the future with complete certainty. The universe is complex, and our knowledge is limited. We can make educated guesses and probabilistic statements, but the future remains fundamentally unknown. What we can do is appreciate the present. Right now, Andromeda is a beautiful spiral galaxy visible in our night sky. Right now, it is the most distant object that can be seen with the naked eye. Right now, it is racing toward us at tremendous speed, yet still separated by a gulf of space so vast that the journey will take billions of years. The experience of observing Andromeda is something every human being can share. On a clear dark night, away from city lights, the galaxy is visible as a faint fuzzy patch in the constellation Andromeda. Binoculars or a small telescope reveal its elongated shape. A larger telescope shows hints of its spiral structure, and the nearby satellite galaxies M32 and M110. Photography with long exposures brings out stunning detail, revealing the spiral arms, the dust lanes, and the bright star-forming regions. When you look at Andromeda, you are looking back in time. The light entering your eyes began its journey 2.5 million years ago, when our ancestors were just beginning to use stone tools. That light traveled through the void of intergalactic space, covering roughly 6 trillion miles every year for 2.5 million years. And now, at this very moment, that ancient light is ending its journey on your retina, transformed into electrical signals that your brain interprets as a faint glow in the sky. There is something profound about this connection across time and space. The photons hitting your eye were emitted by stars that may no longer exist. Some of those stars have likely exploded as supernovae in the intervening millennia. Others may have faded into white dwarfs or burned out entirely. The Andromeda you see is not the Andromeda of today. It is a ghost image, a memory of how the galaxy looked when Earth was inhabited by creatures that were not yet quite human. And yet, on cosmic timescales, 2.5 million years is not very long. Andromeda has not changed dramatically in that time. The spiral arms may have rotated slightly. A few stars have been born and died. But the overall structure, the trillion stars, the dark matter halo, the satellite galaxies, all of these remain essentially the same. The Andromeda of today is almost indistinguishable from the Andromeda we observe. This permanence on human timescales is characteristic of galaxies. Individual stars may come and go, but the galaxy itself persists for billions of years. Andromeda has been recognizable as a spiral galaxy for perhaps 10 billion years or more. It will remain so for billions of years into the future, until its merger with the Milky Way transforms it into something new. The knowledge that Andromeda has been shining in space for longer than our solar system has existed puts our own existence in perspective. When Andromeda formed its first stars, our Sun was not yet a gleam in the eye of any molecular cloud. When Andromeda's spiral arms first took shape, the atoms that would someday form Earth were scattered across the galaxy, forged in the hearts of stars that died long ago. We are latecomers to a universe that was old before we arrived. Andromeda is a reminder of this cosmic antiquity. It was there before us, and it will be there long after we are gone. Its trillion stars shine on, indifferent to the tiny creatures on a small blue planet who have only recently learned to look up and understand what they are seeing. But this cosmic indifference is not cause for despair. It is cause for wonder. We are the universe looking back at itself. Through human eyes and human minds, the cosmos has become aware of its own existence. We are made of star stuff, as Carl Sagan famously said, and we have learned to trace our origins back to the stellar nurseries of galaxies like Andromeda. The heavy elements in our bodies, the carbon in our cells, the oxygen we breathe, the iron in our blood, all of these were forged in the cores of massive stars. When those stars exploded, they seeded space with the raw materials for planets and for life. We are literally children of the stars, connected by an unbroken chain of cause and effect to the cosmic processes that shaped galaxies billions of years ago. Andromeda participated in this cosmic chemistry. Its stars produced heavy elements that enriched its gas. That gas formed new generations of stars and planets. Somewhere in Andromeda, there may be planets with conditions suitable for life. There may even be creatures on those planets looking back at us, wondering about the strange, fuzzy patch in their sky that they know will someday merge with their own galaxy. This possibility of life elsewhere in the universe is one of the most tantalizing questions in science. With 1 trillion stars in Andromeda, there could be billions of planets. Some fraction of those planets may be in the habitable zones of their stars, where liquid water can exist. On some of those potentially habitable worlds, life may have arisen. And on some fraction of those living worlds, intelligence may have evolved. The numbers involved are speculative, but even conservative estimates suggest that Andromeda could harbor millions of planets with conditions favorable for life as we know it. Whether any of those planets actually host life, whether any have developed technological civilizations, remains completely unknown. We have no evidence one way or the other. But the possibility exists, and it is a humbling thought. If intelligent beings do exist in Andromeda, they are too far away for any practical communication. Radio signals traveling at the speed of light would take 2.5 million years to reach them. A response would take another 2.5 million years. Any conversation would span millions of years, far longer than the entire history of human civilization. This isolation is one of the sobering realities of cosmic scale. Even if the universe is teeming with intelligent life, the vast distances between stars and galaxies may make contact impossible. Each civilization may be an island, aware of the possibility of others, but unable to reach them, separated by gulfs of space and time too great to bridge. And yet, we keep looking. We search for signals from other civilizations. We launch probes to the outer reaches of our solar system, carrying messages in case anyone should find them millions of years from now. We study exoplanets, looking for signs of atmospheres that might indicate biological activity. The search for life beyond Earth is one of the great scientific enterprises of our age, driven by an ancient human need to know whether we are alone. Andromeda features in this search, though not prominently. Because of its distance, studying individual planets in Andromeda is beyond our current capabilities. We can detect stars and measure their properties. We can observe giant gas clouds and track their motions. But individual Earth-sized planets around individual sun-like stars are far too small and faint to detect at Andromeda's distance. Within our own galaxy, and in the near future, perhaps within the nearest stars, we may be able to characterize the atmospheres of Earth-like planets. Telescopes now being planned could detect biosignature gases, substances like oxygen and methane that on Earth are produced primarily by life. If we find such signatures on a nearby exoplanet, it would revolutionize our understanding of life's place in the universe. But Andromeda will remain a mystery for a long time to come. We can admire its beauty, measure its properties, and predict its future. But the detailed story of its trillion stars, the countless planets that orbit them, and any life that may exist on those planets will remain hidden from us. We simply do not have the technology to probe such distant worlds. This technological limitation is temporary. Human knowledge and capabilities have grown exponentially over the past few centuries. Technologies that seemed like magic to our ancestors are now commonplace. In a few centuries more, capabilities we cannot imagine may become routine. Perhaps someday, our descendants will find ways to study Andromeda in detail we cannot currently conceive. Or perhaps our descendants will visit Andromeda in person, not literally flying there in spacecraft, for even at nearly the speed of light, the journey would take millions of years. But after the merger of our galaxies, the stars of Andromeda will become part of our own cosmic neighborhood. What was once a distant galaxy will become part of the same enormous stellar city as the descendant stars of our Sun. This long-term perspective is one of the gifts that astronomy provides. It lifts us out of our daily concerns and shows us a bigger picture. The scale of Andromeda, the timescales of galactic merger, the distances involved in cosmic structure. All of these remind us that we are part of something much larger than ourselves. There is comfort in this perspective for some, and existential anxiety for others. The universe does not care about us in any personal sense. The laws of physics operate impartially, governing the motions of galaxies just as they govern the fall of an apple. We are not the center of creation. We are not the purpose for which the universe exists. We are, as far as we can tell, a remarkable accident, conscious matter that has arisen through natural processes on a small rocky planet orbiting an ordinary star in an ordinary galaxy. But this accidental nature does not diminish our significance to ourselves. We create our own meaning. We form connections with each other. We build civilizations and create art. We ask questions about the universe and sometimes find answers. The fact that the universe produced creatures capable of wondering about their own existence is itself remarkable, regardless of whether that production was intended or accidental. Andromeda, shining across the void, is part of the context in which we exist. It was there before our species arose. It will be there, transformed into Milkomeda, long after our species is gone. But right now, in this brief window of cosmic time, we can look up and see it. We can study it, appreciate it, and understand something of what it is. The scientific methods we use to study Andromeda have evolved dramatically over the centuries. Early observers saw only a fuzzy patch of light. They had no way of knowing whether it was a cloud of gas within our own galaxy or something far more exotic. The tools of modern astronomy have peeled back layer after layer of mystery, revealing Andromeda's true nature and scale. Spectroscopy, the study of light broken down into its component colors, was one of the first major breakthroughs. By analyzing the spectrum of light from Andromeda, astronomers could determine what elements were present and how fast the gas and stars were moving. This led to the discovery of Andromeda's rotation, showing that it was a massive spinning structure, not just a static cloud. Photography allowed astronomers to accumulate light over long exposures, revealing details invisible to the eye. The first photographs of Andromeda, taken in the late 1800s, showed hints of spiral structure. Better photographs, taken with larger telescopes, revealed more and more detail. By the early 20th century, astronomers could see individual stars in Andromeda, at least the brightest ones. The development of electronic detectors, first photomultipliers, and later charge-coupled devices, or CCDs, revolutionized astronomy. These devices are far more sensitive than photographic film and can measure light levels precisely. Modern astronomical cameras use CCDs similar in principle to those in your smartphone, but far more sophisticated and sensitive. Space-based telescopes like Hubble have pushed the boundaries even further. Above Earth's atmosphere, which blurs and distorts starlight, telescopes can achieve incredible sharpness. Hubble has photographed Andromeda in stunning detail, resolving individual stars even in the dense central bulge. The Hubble images of Andromeda contain hundreds of millions of stars, each one a sun potentially hosting its own planetary system. Radio telescopes have revealed aspects of Andromeda invisible to optical instruments. At radio wavelengths, astronomers can map the distribution of neutral hydrogen gas throughout the galaxy. This gas is the raw material for star formation and traces the spiral structure beautifully. Radio observations have shown that Andromeda's gas disk extends well beyond the visible stellar disk, indicating that there is fuel for future star formation that has not yet been processed into stars. Infrared observations peer through the dust that blocks visible light. Dust grains in galaxies absorb short wavelength light and re-emit it at longer infrared wavelengths. By observing in the infrared, astronomers can see regions hidden from view at optical wavelengths. The Spitzer Space Telescope, which observed in the infrared, provided important data about star formation in Andromeda and the distribution of warm dust throughout the galaxy. X-ray telescopes detect the hot gas that fills the space between stars. This hot gas is heated by supernova explosions and by the activity around the central black hole. X-ray observations of Andromeda have mapped the distribution of this hot gas and detected numerous X-ray binary stars, systems in which a compact object like a neutron star or black hole is accreting material from a companion star. Each wavelength of light reveals a different aspect of Andromeda. Combining observations from across the electromagnetic spectrum gives a complete picture that no single wavelength could provide. This multi-wavelength approach is now standard in astronomy, with major projects coordinating observations from radio to gamma rays to build comprehensive models of celestial objects. Looking forward, new telescopes and observational techniques will continue to sharpen our view of Andromeda. The James Webb Space Telescope, launched in 2021, is the most powerful space telescope ever built, observing primarily in the infrared. It has already provided stunning images of distant galaxies and will contribute to our understanding of Andromeda and its satellites. Ground-based telescopes are also advancing. The extremely large telescope, currently under construction in Chile, will have a mirror over 39 meters in diameter, dwarfing any existing optical telescope. With adaptive optics to correct for atmospheric distortion, it will achieve sharpness approaching that of space telescopes, while collecting far more light. Such telescopes will be able to study Andromeda in unprecedented detail. Gravitational wave astronomy represents an entirely new way of observing the universe. First demonstrated in 2015 with the detection of merging black holes, gravitational wave observations can probe events invisible to electromagnetic radiation. In the distant future, when the supermassive black holes of Andromeda and the Milky Way finally merge, the gravitational waves produced will be detectable by space-based observatories, if any are still operating then. The progress of astronomy over the past few centuries gives reason for optimism about future discoveries. Each generation has built on the work of previous generations, developing new tools and asking new questions. The Andromeda we understand today is far richer and more complex than the fuzzy patch our ancestors saw. The Andromeda our descendants will understand will be richer still. Let us now consider some of the remaining mysteries about Andromeda. Despite all we have learned, there is much we do not know. Science is always a work in progress, with new observations raising new questions as fast as old questions are answered. One ongoing mystery is the exact nature of dark matter. We know that dark matter exists because of its gravitational effects. We know roughly how much of it there is and how it is distributed, but we do not know what dark matter actually is. Is it made of undiscovered particles? Is it a manifestation of modified gravity? Decades of experiments have searched for dark matter particles without success. The mystery remains unsolved. Andromeda's dark matter halo is one of the best studied in the universe, yet we cannot say what that halo is made of. We can measure its mass, trace its extent, and model its density profile. But the fundamental nature of the substance remains hidden. Solving the dark matter puzzle would revolutionize physics and would deepen our understanding of galaxies like Andromeda. The history of Andromeda also contains gaps. We know a major collision occurred about 2 to 3 billion years ago, but the details are uncertain. What galaxy collided with Andromeda? Where did it come from? How massive was it? These questions can be partially answered through modeling, but the models depend on assumptions that may not be correct. The formation of Andromeda's unusual double nucleus is another puzzle. Near the center of the galaxy, instead of a single concentration of stars around the supermassive black hole, there appear to be two distinct concentrations separated by only a few light years. Various explanations have been proposed, from the remnants of a captured galaxy to an unusual orbital structure of stars. The true explanation remains debated. The future evolution of Andromeda is also uncertain. While the general outline of its merger with the Milky Way is understood, the details depend on measurements that are still being refined. The exact timing of the collision, the severity of the impact, and the final structure of the merged galaxy all depend on factors we cannot yet measure precisely. These uncertainties are not failures of science. They are the frontiers where science is still advancing. Future observations and theoretical developments will address some of these questions. New mysteries will undoubtedly arise to replace the old ones. This is the nature of scientific inquiry, an endless process of discovery and refinement. One particularly interesting frontier involves the satellite galaxies of Andromeda. As mentioned earlier, many of these satellites appear to orbit in a thin plane, a configuration not predicted by simple models of galaxy formation. Understanding why this planar distribution exists could reveal something important about how galaxies form and evolve. Recent observations have mapped the motions of many of Andromeda's satellites with unprecedented precision. Some satellites are orbiting in ways consistent with the planar distribution being a real physical structure. Others are not. The data paint a complex picture that theorists are still working to understand. Similar planar satellite distributions have been found around the Milky Way and other galaxies. If this is a common feature of galaxy formation, it may point to something fundamental that current models are missing. Perhaps satellite galaxies are accreted along cosmic filaments, the strands of matter that connect galaxies in the cosmic web. Perhaps they form in place from material thrown out during major mergers. The answer could have implications for our understanding of galaxy formation across the universe. The cosmic web itself is worth pausing to appreciate. Galaxies are not scattered randomly through space. They are organized into a vast network of filaments and walls surrounding enormous empty voids. This structure formed through the action of gravity on the tiny density variations present in the early universe. Regions slightly denser than average attracted more matter, becoming denser still, eventually forming the galaxies and clusters we see today. Andromeda sits at a node in this cosmic web, near the intersection of several filaments. The local group occupies a relatively modest position, on the outskirts of the Virgo supercluster, rather than at its center. We are suburban residents of the cosmic metropolis, looking inward at the bright lights of the Virgo cluster and outward at the vast, empty spaces between superclusters. The cosmic web extends throughout the observable universe. Surveys have mapped its structure out to billions of light-years, revealing a foam-like pattern of walls and voids. The largest structures in the universe, the great walls and filaments that stretch for hundreds of millions of light-years, are part of this web. Andromeda is a small piece of a much larger tapestry. Understanding how galaxies like Andromeda relate to this larger structure is an active area of research. Galaxy properties correlate with environment. Galaxies in dense clusters tend to be different from galaxies in empty voids. The relationship between a galaxy and its surroundings affects its evolution, its star formation rate, and its ultimate fate. Andromeda exists in a relatively benign environment. The local group is not particularly dense or particularly sparse. We are not being torn apart by the tidal forces of a giant cluster, nor are we isolated in a lonely void. This middle-of-the-road environment may have allowed both Andromeda and the Milky Way to develop and maintain their beautiful spiral structures for billions of years. In denser environments, spiral galaxies often lose their gas and have their structures disrupted by interactions with other galaxies. Many of the galaxies in the Virgo cluster, for example, have had their spiral arms stripped away, leaving only the central bulge behind. These transformed galaxies, called lenticular galaxies, represent what happens when spirals experience rough neighborhoods. Andromeda has been able to avoid this fate because of its relative isolation. With the Milky Way as its only major neighbor, it has not experienced the constant harassment that cluster galaxies endure. The occasional merger with a smaller galaxy has actually helped Andromeda grow, providing fresh gas and triggering episodes of star formation. But this isolation will not last forever. Eventually, Andromeda and the Milky Way will merge, and the local group as we know it will be transformed. The resulting giant elliptical galaxy will dominate its surroundings even more completely than Andromeda does today. Smaller galaxies in the local group will be absorbed over time, building up the mass of the central giant. Further in the future, even the broader structure of the universe will change. The universe is expanding, and that expansion is accelerating due to a mysterious phenomenon called dark energy. In the far distant future, galaxies beyond the local group will be carried away from us faster than light can travel. We will be left in an isolated island universe, cut off from the rest of creation. This ultimate fate lies trillions of years in the future, far beyond any timescale relevant to human concerns. But it is part of the story of Andromeda and our place in the cosmos. The galaxies we see today will not always be visible. The cosmic web that connects them will one day be stretched beyond recognition. Only locally bound groups, like the merged remnant of the local group, will remain as islands of matter in an ever-expanding sea of space. For now, though, we live in a universe rich with galaxies. The night sky offers countless wonders for those who take the time to look. Andromeda is just one of those wonders, albeit a special one due to its proximity and its connection to our own future. Observing Andromeda requires no special equipment, just dark skies and patience. From a location free of light pollution, the galaxy is visible to the naked eye as a faint, elongated smear of light. Binoculars reveal its oval shape and perhaps hints of its satellite galaxies. A small telescope shows more detail, though the galaxy's size means that the entire structure often does not fit in a single field of view. Amateur astronomers around the world observe and photograph Andromeda regularly. With modern cameras and image processing techniques, amateurs can produce stunning images that would have amazed professional astronomers a generation ago. The democratization of astronomy has brought the wonders of the universe within reach of anyone with curiosity and modest equipment. The location of Andromeda in the sky makes it accessible to observers in the northern hemisphere for most of the year. It lies in the constellation Andromeda, which itself is named after the princess of Greek mythology, who was chained to a rock and rescued by Perseus. The constellation is near the familiar W shape of Cassiopeia and the Great Square of Pegasus. Once you know where to look, finding the galaxy is straightforward. The best time to observe Andromeda is during the autumn and winter months in the northern hemisphere, when the constellation is high in the evening sky. At these times, Andromeda can be visible from dusk until dawn, giving observers many hours to study and photograph it. Even a brief glance on a dark night is enough to spark wonder at the scale of what you are seeing. Photography reveals what the eye cannot easily detect. Long exposure images bring out the spiral, arms, the dust lanes, and the star-forming regions. Color images show the difference between the blue young stars in the arms and the redder old stars in the bulge. Careful processing can reveal the faint outer regions of the galaxy and even the streams of stars in its halo. Professional astronomers have created mosaic images of Andromeda that contain hundreds of millions of pixels, resolving billions of individual stars. These images are scientific datasets as well as stunning works of art. Astronomers use them to map star formation, trace chemical abundances, and study stellar populations across the entire galaxy. One particularly impressive effort is the panchromatic Hubble Andromeda Treasury, known as PHAT. This survey observed about 1/3 of Andromeda's disk, with the Hubble Space Telescope producing images in ultraviolet, optical, and near-infrared light. The resulting dataset contains measurements of over 100 million stars, the largest stellar survey of any galaxy except our own Milky Way. The PHAT survey has enabled detailed studies of star formation history across Andromeda's disk. By analyzing the colors and brightnesses of stars, astronomers can determine when different regions of the galaxy experience bursts of star formation. The results paint a picture of an active and dynamic galaxy, with star formation rates varying across space and time. Similar surveys are planned for other galaxies, but Andromeda's proximity makes it uniquely suited for such detailed study. No other large spiral galaxy is close enough for individual stars to be resolved in such numbers. The information gleaned from Andromeda informs our understanding of spiral galaxies everywhere. The relationship between professional and amateur astronomy is closer than in many sciences. Amateur observers contribute to professional research in several ways. Some monitor variable stars or search for supernovae. Others produce high-quality images that supplement professional observations. The line between amateur and professional is often blurred, with passionate hobbyists contributing meaningful data to the scientific community. This collaborative spirit extends to the study of Andromeda. Citizen science projects have engaged the public in classifying features in Andromeda images or measuring the properties of star clusters. These projects take advantage of human pattern recognition abilities, which still outperform computers for certain tasks, while spreading the workload across many participants. The study of Andromeda connects us to the broader human quest to understand the universe. Every culture throughout history has looked up at the night sky and wondered what lay beyond. The stars and the fuzzy patch in Andromeda sparked questions that have only recently begun to be answered. In understanding Andromeda, we continue a tradition stretching back to the first humans who gazed at the heavens. The Persian astronomer Abd al-Rahman al-Sufi made the first recorded description of Andromeda in the year 964. He called it a small cloud in his Book of Fixed Stars. For nearly 1,000 years after that, people observed the same small cloud without understanding what it truly was. Only in the past century have we learned that this small cloud is actually a vast galaxy of 1 trillion stars. The progress of knowledge is not inevitable. It required generations of scientists building on each other's work, developing new technologies, and testing ideas against observations. The story of how we came to understand Andromeda is a story of human ingenuity and persistence. It reminds us that mysteries can be solved if we are willing to look carefully and think deeply. There remain mysteries that may never be solved. What lies beyond the observable universe? Are there other universes entirely? Is there intelligent life in Andromeda looking back at us? Some questions may exceed the limits of what can be known through observation, but even these limits are not fixed. What seems unknowable today may become knowable with technologies and ideas not yet imagined. Andromeda will continue to be studied as long as human civilization endures. New telescopes will reveal new details. New theories will explain old puzzles. New generations will look up at that faint fuzzy patch and feel the same sense of wonder that has captivated observers for millennia. The scale of Andromeda, truly understood, changes how we see ourselves. We are inhabitants of a galaxy that is itself merely average, one of countless spirals scattered through the cosmic web. Our galaxy is destined to merge with a larger neighbor, being absorbed into a structure that will persist for trillions of years. On these scales, human history is the blink of an eye, a brief moment of awareness in an unimaginably vast and ancient universe. And yet, this brief moment is ours. We are here now, capable of understanding what we see. We can measure the distance to Andromeda, calculate its mass, predict its future. We can appreciate its beauty through photographs and personal observation. We can feel the profound connection between the atoms in our bodies and the stellar furnaces that created them. This awareness, this ability to look up and wonder, is precious. It is, as far as we know, rare in the universe. We should cherish it. The gravitational bond between Andromeda and the Milky Way represents one of the most significant relationships in our cosmic neighborhood. These two galaxies have been influencing each other for billions of years, their mutual gravity shaping their trajectories through space. Long before they physically touch, their gravitational fields have been entwined, each one pulling on the other across the vast gulf of intergalactic space. Consider for a moment the nature of gravity. It is the weakest of the four fundamental forces, yet on cosmic scales, it is the only force that matters. Electromagnetism is stronger, but positive and negative charges tend to cancel out on large scales. The strong and weak nuclear forces operate only at subatomic distances. Gravity, though feeble compared to these other forces, extends forever and never cancels out. Mass always attracts mass. The gravitational attraction between Andromeda and the Milky Way has been pulling the two galaxies together since long before either galaxy existed in its current form. Back when both were smaller collections of matter, still assembling from the primordial soup of the early universe, they were already feeling each other's pull. As they grew larger and more massive through mergers and accretion, the gravitational force between them strengthened. Today, that gravitational force acts across 2.5 million light-years of space. The strength of gravity decreases with the square of the distance, So by the time it reaches us from Andromeda, it is incredibly weak, and yet it is enough. Over billions of years, even a weak force can do enormous work. The acceleration toward Andromeda is imperceptible on human timescales, but integrated over cosmic time, it adds up to hundreds of kilometers per second of velocity. The concept of escape velocity helps illustrate this gravitational relationship. For any gravitationally bound system, there is a speed above which objects can escape to infinity and never return. Earth's escape velocity is about 11 kilometers per second. The Sun's escape velocity from Earth's distance is about 42 kilometers per second. The Milky Way's escape velocity from the Sun's position is perhaps 500 kilometers per second. The escape velocity from the combined gravity of the local group is higher still. Both Andromeda and the Milky Way contribute to holding the local group together. At our position, we are gravitationally bound not just to the Milky Way, but to the entire structure. We cannot escape to infinity. We are, in a very real sense, prisoners of our cosmic neighborhood, destined to fall inward toward the growing mass concentration at the center. This gravitational imprisonment is not something to fear. It is simply the nature of the universe. Everything in the cosmos is bound to something. Planets are bound to stars. Stars are bound to galaxies. Galaxies are bound to clusters and groups. Only at the larger scales, between superclusters, does the expansion of the universe overcome gravity. At smaller scales, gravity binds matter together into persistent structures. The gravitational potential energy stored in the Andromeda Milky Way system is enormous. As the two galaxies fall together, this potential energy is converted into kinetic energy, increasing their relative velocity. When they finally merge, this kinetic energy is distributed among the stars, randomizing their orbits and heating the stellar population. The orderly rotation of spiral disks is converted into the chaotic motions characteristic of elliptical galaxies. This conversion of gravitational potential energy into stellar kinetic energy is a fundamental process in galaxy evolution. Every major merger transforms energy in this way. The end result is always a puffier, more spheroidal structure, unless there is enough gas left over to form a new disk. In the Andromeda Milky Way merger, there probably will not be much gas left by the time the merger completes. Both galaxies will have exhausted most of their star-forming fuel, leaving behind a dead elliptical galaxy with little ongoing star formation. The structure of this future galaxy, Milkomeda, can be predicted using computer simulations. These simulations model the gravitational interactions of millions or billions of particles representing stars and dark matter. By running these simulations forward, in time, astronomers can see how the merger unfolds and what the final product looks like. The simulations consistently predict that Milkomeda will be a giant elliptical galaxy, roughly spheroidal in shape and containing several trillion stars. The spiral arms of both parent galaxies will be destroyed within 1 billion years of the first close passage. Long tidal tails of stars will be flung outward during the merger, creating spectacular structures that may persist for billions of years before finally falling back and being absorbed. The central regions of Milkomeda will be dense and luminous, dominated by old red stars from the merged bulges of both galaxies. The supermassive black hole at the center will be more massive than either of the original black holes, having grown through the merger and perhaps through the accretion of gas stirred up during the collision. This black hole will be quiescent for most of Milkomeda's existence, but may occasionally flare to life if matter falls into it. The stellar halo of Milkomeda will contain the debris of the merger, streams of stars from tidally disrupted structures, ancient globular clusters from both parent galaxies and possibly the remnants of dwarf galaxies that were absorbed along the way. This halo will extend for hundreds of thousands of light years, a sparse but vast envelope of ancient stars surrounding the denser central regions. Within Milky individual stars will continue their existence largely unaffected by the merger. Stars do not collide during galactic mergers because they are too widely spaced. A star like our Sun will be flung into a new orbit, perhaps much farther from the galactic center, perhaps on a more elliptical path, but it will continue to shine and host its planets as if nothing had happened. This is a comforting thought, even if Earth itself will be uninhabitable long before the merger completes. Any civilizations that exist on planets around stars in either galaxy could potentially survive the merger, watching the spectacular show from a safe distance. Their night skies would be transformed beyond recognition, but their physical existence would not be threatened. Of course, the timescales involved make it unlikely that any currently existing civilization will witness the merger. By the time Andromeda arrives, over 4 billion years will have passed. The Sun will have evolved into a red giant and then a white dwarf. Earth will have been rendered uninhabitable for billions of years. Any descendants of humanity will have had to relocate to other worlds around other stars. It is interesting to speculate about what those distant descendants might be like. 4 billion years is an immense span of time. Life on Earth 4 billion years ago was barely getting started, single-celled and primitive. The evolutionary changes over the next 4 billion years are impossible to predict. Our descendants might be unrecognizable to us, perhaps no longer biological at all. Such speculation lies outside the bounds of science, but it adds to the wonder of contemplating Andromeda's scale. We are not just learning about a distant galaxy. We are learning about our own cosmic future, about the forces that will shape whatever comes after us, about the structures that will persist long after humanity as we know it is gone. The merger with Andromeda is not an ending. It is a transformation. The atoms that make up our bodies, forged in ancient stars, will continue to exist. They will be incorporated into new stars and new planets in Milky Way. Some may end up in the cores of stars, fused into heavier elements. Others may drift in the interstellar medium for eons. The matter is never destroyed, only rearranged. This continuity of matter provides a strange kind of immortality. We are temporary patterns in an eternal flux of particles. The particles themselves will outlast us, participating in cycles of creation and destruction that span billions of years. In some diffuse sense, parts of what we are will still exist when Milky Way forms, even if consciousness and individual identity are long gone. The philosophical implications of cosmic scale are profound. Andromeda challenges our intuitions about importance and permanence. In the face of such vastness, human concerns can seem trivial. Wars, politics, personal dramas, all of it fades to insignificance against the backdrop of galactic evolution. And yet, it is precisely because we are insignificant in cosmic terms that our significance to each other matters so much. Different people draw different conclusions from contemplating the cosmic scale. Some feel humbled and small. Others feel liberated, freed from the burden of cosmic importance. Some find comfort in the idea that the universe will go on without us. Others feel despair at the same thought. There is no single correct response. The universe does not come with instructions for how to feel about it. What science can tell us is what the universe is like. It can describe the properties of Andromeda, the dynamics of galactic mergers, the structure of the cosmic web. It cannot tell us what this means for how we should live? That is a question each person must answer for themselves, drawing on whatever philosophical, spiritual, or personal resources they find meaningful. For many, the scientific picture of the universe is itself a source of meaning and wonder. The fact that the universe is comprehensible, that human minds can grasp something of its structure and history, is remarkable. We are not passive observers of an incomprehensible chaos. We are active participants in a cosmos that obeys elegant mathematical laws and has produced structures of breathtaking complexity and beauty. Andromeda is one of those structures. It is not just a collection of stars and gas. It is a pattern in the cosmic substrate, a concentration of matter that has persisted for billions of years, growing and evolving through processes we are only beginning to understand. Time, ones. It is connected to us, gravitationally and historically, sharing a common origin in the aftermath of the Big Bang. The light from Andromeda that reaches our eyes tonight is the same light that reached the eyes of ancient Babylonians and Greeks, though they had no idea what they were seeing. It will continue to reach the eyes of future generations for as long as anyone is there to look. This continuity of observation connects us across time, a shared experience spanning millennia and potentially millions of years to come. The history of understanding Andromeda mirrors the history of human knowledge more broadly, from mysterious fuzzy patch to nebula to external galaxy to approaching merger partner. Our understanding has evolved in fits and starts, driven by new technologies and new ideas. Each generation has added to the sum of knowledge, building on the achievements of those who came before. This progress is not guaranteed to continue. Civilizations can collapse, knowledge can be lost, humanity could destroy itself through war or environmental catastrophe. The universe does not care whether we survive. But if we do survive, and if we continue to value knowledge and inquiry, then our understanding of Andromeda and the universe will continue to deepen. The challenges facing humanity today are real and urgent. Climate change, nuclear weapons, pandemic diseases, artificial intelligence, these are existential risks that demand our attention. Contemplating Andromeda does not solve these problems, but it does provide perspective. It reminds us that we are part of something larger than our immediate concerns. It encourages long-term thinking and an appreciation for the fragility and preciousness of our existence. Some argue that space exploration and astronomical research are luxuries we cannot afford when there are pressing problems on Earth. Others argue that these endeavors are essential to our long-term survival and sense of purpose. The debate will continue, and reasonable people can disagree. What seems clear is that understanding the universe has value beyond any immediate practical application. It is part of what makes us human. Andromeda calls to us across the void. Not literally, of course. There are no messages in the light from a trillion stars, but there is a kind of cosmic invitation, a reminder that there is more to existence than the surface of a single planet. We are children of the stars, living on a world that orbits one star among billions, in a galaxy that will merge with another galaxy in a cosmic dance of almost unimaginable grandeur. Whether we accept this invitation, whether we reach out toward the stars or remain content on our small world, is up to us. The universe offers possibilities. It does not compel choices. Andromeda will continue on its path, regardless of what we decide. But for those who choose to look up and wonder, the galaxy next door is always there, shining across the distance, waiting to be understood. The true scale of Andromeda, finally grasped, reveals a universe of astonishing scope, a galaxy spanning 220,000 light-years, a dark matter halo extending 1 to 2 million light-years, a trillion stars, countless planets, and possibly other forms of life pondering their own cosmic surroundings. An approach velocity of hundreds of kilometers per second, a merger timeline measured in billions of years, a resulting structure that will endure for trillions of years more. These numbers are almost meaningless in isolation. No human mind can truly comprehend what a trillion means, or what 2 million light-years feels like. We can only use analogies, comparisons, and calculations to approximate understanding. We know that Andromeda is vastly larger than anything in our everyday experience. We know that it is approaching and will eventually merge with our galaxy. We know that this is a natural part of cosmic evolution, neither catastrophe nor miracle. What we do with this knowledge is up to us. We can ignore it, going about our daily lives as if the cosmos beyond Earth does not exist. We can use it to inspire art, literature, and philosophy. We can pursue it through scientific research, telescopic observations, and space exploration. We can teach it to our children, passing on the wonder to future generations. Andromeda will be there for all of these responses. It shines on, indifferent but available, a cosmic laboratory and a source of endless fascination. It is close enough to study in detail, far enough to embody the vastness of space. It is approaching slowly enough that we need not panic, fast enough that its motion can be measured. It is, in many ways, the perfect object for contemplating the scale of the universe. The story of Andromeda is not over. It continues every moment as light travels toward us, as stars are born and die, as dark matter halos interact, as gravity draws the galaxies together. We are privileged to live at a time when we can understand something of this story, when we have the tools to measure and the theories to interpret. Previous generations could only wonder. Future generations may take this knowledge for granted. We are at a special moment, a turning point in human understanding of our cosmic context. Let us appreciate this moment fully. Let us recognize the scale of what surrounds us and find within it whatever meaning resonates with our individual hearts and minds. The universe is vast and old and indifferent, but it is also beautiful and comprehensible and full of wonder. Andromeda embodies all of these qualities. It is a gift to those who take the time to understand it. As we reach the culmination of our exploration, let us bring together everything we have discovered about the true scale of Andromeda. We began with a question that seems simple on the surface. How big is the Andromeda Galaxy? But, as we have seen, the answer is anything but simple. It depends on what we measure and how we define the boundaries of a galaxy. The visible stellar disk of Andromeda spans approximately 220,000 light-years. Within this disk, roughly 1 trillion stars orbit the galactic center, more than double the number in our own Milky Way. The central bulge alone contains hundreds of billions of old red stars packed into a region tens of thousands of light-years across. This visible component is what most people picture when they think of Andromeda, and even this is almost incomprehensibly vast. But the visible disk is only the beginning. Surrounding it is a hot gaseous halo that extends for at least 1 million light-years from the galaxy's center. This halo contains as much mass in gas as half the stars in the visible galaxy. It is being constantly enriched by supernovae within the disk, accumulating heavy elements over billions of years. And beyond even this gaseous envelope lies the dark matter halo, extending perhaps 2 million light-years, containing the majority of the galaxy's total mass. When we account for all of this, the true scale of Andromeda becomes staggering. The galaxy we see with our eyes or our telescopes is merely the bright core of a much larger structure. The dark matter that dominates the mass extends so far that it nearly reaches the dark matter halo of our own Milky Way. In a very real sense, the two galaxies are already touching, even though their visible components are still separated by over 2 million light-years. This extended structure fundamentally changes how we should think about galaxies. They are not isolated islands of stars floating in empty space. They are vast, diffuse concentrations of matter, mostly invisible, extending far beyond what any photograph can capture. The beautiful spiral arms and glowing nebulae that we admire in images are like the tip of an iceberg, hinting at the enormous mass hidden below the surface. The mass of Andromeda, including both visible and dark matter, is estimated to be between 800 billion and 1 trillion times the mass of our Sun. Recent studies suggest that previous estimates may have been too high, with the true mass perhaps closer to 450 billion solar masses. But even this revised figure represents more mass than the human mind can truly grasp. Our Sun, a star so large that over 1 million Earths could fit inside it, is just one unit in this cosmic accounting. The velocity of Andromeda's approach adds another dimension to its scale. At roughly 110 kilometers per second, the galaxy is racing toward us faster than any human-made object has ever traveled. This velocity represents the conversion of gravitational potential energy into motion, the same principle that makes a falling apple accelerate toward the ground. But here, the apple is a trillion-star galaxy, and the ground is another trillion-star galaxy, and the acceleration has been happening for billions of years. The timeline of the eventual merger stretches our comprehension of time just as the physical dimensions stretch our comprehension of space. Current estimates suggest the first close passage will occur in about 4 billion years, with the full merger completing perhaps 7 billion years from now. These numbers are so large that they lose meaning. 4 billion years ago, the most complex life on Earth was single-celled organisms. 7 billion years is longer than our solar system has existed. Within this cosmic context, the local group represents our immediate neighborhood. This collection of more than 80 galaxies spans about 10 million light-years, with Andromeda and the Milky Way as its two dominant members. The gravitational influence of these two giants shapes the motions of every smaller galaxy in the group. Dwarf galaxies fall toward one or the other, are absorbed or disrupted, and contribute their stars to the ever-growing halos of the major players. The local group itself is part of the Virgo supercluster, a collection of at least 100 galaxy groups and clusters spanning about 110 million light-years. At the center of this supercluster lies the Virgo cluster, containing over 2,000 galaxies, including giant ellipticals far larger than Andromeda. From the perspective of the Virgo supercluster, the local group is a minor outlying structure, and Andromeda is just another moderately sized spiral galaxy. And the Virgo supercluster is itself part of an even larger structure called Laniakea, spanning over 500 million light-years. Laniakea contains an estimated 100,000 galaxies, all being drawn toward a region called the Great Attractor. At this scale, Andromeda is almost invisible. One galaxy among multitudes, its trillion stars just a tiny fraction of the matter in the supercluster. Yet despite this cosmic perspective, Andromeda remains special. It is the closest large galaxy to our own. It is the most distant object visible to the unaided human eye. It is the galaxy destined to merge with ours, transforming the structure of our cosmic home. Among all the galaxies in the universe, Andromeda is the one most intimately connected to our own fate. The experience of seeing Andromeda with your own eyes connects you to something profound. On a clear, dark night, away from city lights, that faint, fuzzy patch of light is visible in the constellation Andromeda. The photons entering your eye have traveled for 2.5 million years, crossing the void of intergalactic space at the speed of light. Those photons were emitted by stars that may no longer exist, from a galaxy that has changed in subtle ways since the light left. To see Andromeda is to look back in time. The light reaching us now shows the galaxy as it was, when our ancestors were still learning to make stone tools. The Andromeda of today, at this very moment, is different. Stars have been born and died. The galaxy has rotated on its axis. The distance between us has decreased by a small but measurable amount. But we will not see today's Andromeda for another 2.5 million years. This time delay is one of the strange consequences of cosmic scale. We can never see the universe as it is right now. We can only see the past, with the delay increasing with distance. The most distant galaxies we can observe are seen as they were over 13 billion years ago, when the universe was young and galaxies were just beginning to form. Andromeda, relatively nearby, shows us the more recent past, but still a past far removed from any human experience. The realization that we are witnessing ancient light has profound implications. Everything we observe in the universe is historical information. Our picture of the cosmos is a composite of different eras, assembled from light that left its sources at different times. The universe we piece together from these observations is not a snapshot, but a montage, a collection of moments spread across billions of years. Andromeda features in this cosmic montage as one of the nearest and most detailed pieces. Because it is relatively close, the time delay is only 2.5 million years, short enough that the galaxy has not changed dramatically. We can be confident that the Andromeda of today is fundamentally similar to what we observe. The same trillion stars, the same dark matter halo, the same approach velocity. The details may have shifted, but the essential nature remains. This reliability makes Andromeda an invaluable laboratory for studying galaxy structure and evolution. We can observe individual stars, map the distribution of gas, track the motions of satellite galaxies. We can test our theories about how galaxies form and evolve against detailed observations that would be impossible for more distant systems. Andromeda serves as a bridge between our intimate knowledge of the Milky Way and our more superficial understanding of the broader galaxy population. The supermassive black hole at the center of Andromeda represents another aspect of cosmic scale. With a mass of roughly 100 million suns, this black hole is a monster by any standard. Yet compared to the trillion stars and the dark matter halo surrounding it, the black hole is almost insignificant, a tiny concentration of mass at the heart of a vastly larger structure. Black holes command our imagination because of their extreme properties, but in the context of galactic structure, they are almost minor features. When Andromeda and the Milky Way finally merge, their central black holes will also merge. This process will unfold over millions of years as the two black holes spiral toward each other, losing energy through gravitational radiation. The final coalescence will release an enormous burst of gravitational waves, ripples in the fabric of space-time that will propagate outward at the speed of light. This event will mark the final act in the merger, the coming together of two cosmic giants into a single, more massive structure. The merged galaxy, Milky Way, will be our descendants' home, assuming any descendants exist by then. It will be a giant elliptical galaxy, lacking the beautiful spiral arms that currently characterize both Andromeda and the Milky Way. The orderly rotation of the parent galaxies will be replaced by the random motions of stars on eccentric orbits. The night sky, from any planet within Milkomeda, will be filled with a diffuse glow of countless stars rather than the distinct band of the Milky Way or the spiral form of Andromeda. For beings living in Milkomeda, the history of the merger will be ancient. They may have records or legends of a time when two separate galaxies existed, or the merger may be so far in the past that all memory of it has faded. The timescales involved are so vast that prediction becomes impossible. What we can say is that matter endures. The atoms that now compose our bodies, our planet, our sun, will still exist in Milkomeda. They will have been recycled through new generations of stars, perhaps multiple times. But matter is never destroyed, only transformed. This cosmic recycling connects us to the universe in a deeply physical way. We are made of material that was forged in stars, scattered by supernovae, and collected by gravity into new stellar systems. The iron in our blood was created in the heart of a massive star that exploded billions of years ago. The oxygen we breathe was synthesized in similar stellar furnaces. We are, quite literally, children of the cosmos, temporary patterns in an eternal flow of matter and energy. Andromeda is part of this cosmic story. Its stars have produced heavy elements that enrich its gas. That gas forms new generations of stars and planets. On some of those planets, life may have arisen. Beings who ponder their own origins and wonder about the fuzzy patch of light visible in their night sky. The universe may be filled with such ponderers, each one a unique perspective on the cosmic drama, each one connected to all the others by shared origins and shared physics. We may never know if life exists in Andromeda. The distance is too great for any form of communication we can currently imagine. Radio signals would take 2.5 million years to cross the gap, and a reply would take equally long. By the time any such conversation could occur, countless generations would have passed. The time delay that allows us to observe Andromeda's past also isolates us from any present inhabitants. This isolation is one of the melancholy aspects of cosmic scale. The universe may teem with intelligent life, yet each island of consciousness may be forever separated from the others by gulfs of space and time. We can observe, we can wonder, we can hope, but we cannot connect. The stars shine on, indifferent to the minds that contemplate them. And yet, there is also hope in this cosmic perspective. The same processes that created life on Earth could create life elsewhere. The same elements, the same chemistry, the same physical laws operate throughout the universe. If life arose once, it could arise many times. The universe is vast enough and old enough for countless experiments in biology. Even if we never meet other beings, we can take comfort in the probability that we are not alone. Andromeda reminds us of both our isolation and our connection. It is impossibly far away, yet gravitationally bound to us. It is populated by 1 trillion alien suns, yet made of the same elements as our own world. It is ancient beyond comprehension, yet we can observe it and understand something of what it is. In studying Andromeda, we learn about ourselves and our place in a universe that is both indifferent and wondrous. The true scale of Andromeda, when finally grasped, changes how we see everything. The daily concerns that occupy our attention shrink to insignificance against the backdrop of galactic evolution. Yet at the same time, those daily concerns gain a new preciousness. We are rare, perhaps unique, certainly special in some sense. The universe produced creatures capable of looking up and understanding what they see. That is remarkable, regardless of how vast or old the cosmos may be. As we conclude our exploration, let us return one final time to that faint fuzzy patch visible on a dark night. Find a location away from city lights. Let your eyes adjust to the darkness. Look toward the constellation Andromeda, below the distinctive W shape of Cassiopeia. There, if conditions are right, you will see it. A smudge of light, barely perceptible, easy to miss if you do not know where to look. That smudge is the combined glow of 1 trillion suns. It is a galaxy larger than our own, approaching at tremendous speed, destined to merge with our cosmic home. It is surrounded by an invisible ocean of dark matter extending for millions of light years. It has been forming stars for billions of years and will continue for billions more. It contains mysteries we have not yet solved and wonders we have not yet imagined. Looking at Andromeda, you are looking at your future, in a cosmic sense. The atoms in your body will still exist when Milky forms. They will be scattered among the stars, incorporated into new worlds, perhaps part of new life forms. The matter endures, even as patterns come and go. In this way, we are connected to the deepest past and the farthest future, bound by physics to a universe that brought us into being. The true scale of Andromeda is not just a matter of numbers and measurements. It is a gateway to understanding our cosmic context, our origin, and our destiny. It is a reminder that we are part of something much larger than ourselves, something ancient and beautiful and vast beyond imagining. It is an invitation to wonder, to explore, to reach beyond the familiar and touch the infinite. If you have found this journey through the scale of Andromeda fascinating, take a moment to subscribe to the channel and hit that like button. Your support helps bring more content like this, exploring the wonders of our universe and our place within it. Share this with someone who might appreciate the cosmic perspective. And leave a comment below, letting us know what aspect of Andromeda's scale amazed you the most. The Andromeda Galaxy awaits your gaze. On the next clear night, step outside and look up. Find that faint fuzzy patch and remember what you have learned. You are looking at 2.5 million years of light travel. You are looking at 1 trillion stars. You are looking at the future of your cosmic home. You are looking at the true scale of Andromeda. Thank you for watching, and we will see you in the next one. There are moments in scientific history when a single observation changes everything. The discovery that Andromeda was a separate galaxy, not a nebula within the Milky Way, was one such moment. Before Edwin Hubble's measurements in the 1920s, the universe was thought to be much smaller than it actually is. The Milky Way was considered to be the entire cosmos, a single island of stars in an otherwise empty void. Andromeda's true nature shattered this cozy picture and opened humanity's eyes to a universe of staggering immensity. That paradigm shift happened less than a century ago. Within living memory, our conception of the cosmos has expanded from a single galaxy to billions of galaxies, from thousands of light years to billions of light years. The scale of Andromeda, which seems so vast to us today, was utterly unknown to our great-grandparents. What will our great-grandchildren discover that will make our current knowledge seem equally provincial? The evolution of astronomical knowledge has always been a story of expanding horizons. Ancient astronomers measured the size of the Earth and the distance to the Moon. Later generations calculated the distance to the Sun and the sizes of the planets. The distance to nearby stars was measured in the 19th century. The distance to Andromeda was measured in the 20th century. Each new measurement revealed a universe larger than previously imagined. This pattern of expanding knowledge shows no sign of stopping. Current research is pushing toward understanding the most distant galaxies, the structure of space-time itself, and the nature of dark matter and dark energy. Future discoveries may reveal aspects of the cosmos we cannot currently imagine. Andromeda will remain an important subject of study, a nearby example of galactic structure that can be examined in unprecedented detail as our technology improves. The relationship between Andromeda and the Milky Way represents a natural experiment in galactic dynamics. We are embedded within one participant of this cosmic dance, giving us an intimate view of how a spiral galaxy works. At the same time, we can observe the other participant from the outside, seeing its structure as a whole. This dual perspective is scientifically invaluable. It allows us to connect what we see happening around us with what we observe in the external galaxy. Consider the spiral arms, for example. Within the Milky Way, we are located in a spur off one of the major spiral arms. We can observe the gas and stars around us, tracking their motions and mapping their distribution. But seeing the overall spiral pattern from within is extremely difficult, like trying to understand the layout of a forest while standing among the trees. Andromeda gives us the aerial view that we lack for our own galaxy. We can see its spiral arms clearly, trace their structure, and understand how they relate to the underlying disk. Similarly, the central bulge of the Milky Way is hidden from direct observation by intervening dust clouds. We can study it using infrared and radio waves that penetrate the dust, but visible light observations are largely blocked. In Andromeda, the bulge is fully exposed to our view. We can photograph it directly, measure its stellar population, and study its structure in ways that are impossible for our own galaxy. This complementary relationship between the two galaxies has driven much of our understanding of spiral structure. Theories developed to explain what we observe in Andromeda can be applied to the Milky Way and vice versa. The two galaxies serve as laboratories for testing ideas about how spiral arms form, how stars migrate through galactic disks, how central black holes grow, and how dark matter halos influence visible structure. The dark matter halos of both galaxies remain largely mysterious despite decades of study. We know they exist because of their gravitational effects. We know roughly how much mass they contain and how far they extend. But the fundamental nature of dark matter remains unknown. Is it made of undiscovered particles? Is it a manifestation of some modification to our understanding of gravity? Experiments around the world are attempting to detect dark matter particles directly, so far without success. Andromeda's dark matter halo is one of the best studied in the universe. Its mass can be estimated from the motions of satellite galaxies and the rotation of gas in the outer disk. Its extent can be inferred from gravitational lensing observations. Yet for all this study, we still cannot say what dark matter actually is. The mystery that began with observations of Andromeda in the 1970s remains unsolved today. Resolving the dark matter mystery would represent another paradigm shift in our understanding of the cosmos. It would reveal new physics, potentially connecting cosmology to particle physics in unexpected ways. The scale of Andromeda's dark matter halo, extending for perhaps 2 million light years, would take on new meaning once we understand what that halo is made of. Current estimates of mass and extent would be refined. Our picture of galactic structure would become sharper and more complete. The tools available for studying Andromeda continue to improve. The next generation of extremely large ground-based telescopes will resolve individual stars throughout Andromeda's disk with unprecedented clarity. Space-based observatories will provide views at wavelengths inaccessible from the ground. Gravitational wave detectors may eventually become sensitive enough to observe the final merger of the central black holes, though that event lies billions of years in the future. Each new observation adds to our understanding. The picture of Andromeda that emerges is not static, but constantly evolving, refined by each new data set. What we know today is more complete than what was known a decade ago, and what will be known a decade hence will be more complete still. Science progresses through this accumulation of observations, always tentative, always open to revision, but steadily approaching a more accurate picture of reality. The scale of Andromeda teaches us humility. We are small creatures on a small planet orbiting an ordinary star in an ordinary galaxy. There are structures in the universe vastly larger than anything we can build or even fully comprehend. The forces shaping galactic evolution operate on timescales that dwarf the entire span of human history. Against this backdrop, our concerns and achievements seem almost inconsequential. And yet, humility need not imply insignificance. We are the universe becoming aware of itself. Matter organized in patterns complex enough to contemplate its own origins. The fact that we can measure the distance to Andromeda, calculate its mass, predict its future, is itself remarkable. We are small, but we are capable of understanding large things. We are brief, but we can contemplate eternity. The true scale of Andromeda, finally, is not just a matter of physical dimensions. It is a scale of meaning, of significance, of our relationship to the cosmos that gave us birth. To grasp this scale is to undergo a transformation in perspective, to see ourselves and our world in a new light. It is to join a long tradition of stargazers who have looked up and wondered, each generation adding its insights to the accumulated wisdom of humanity. Andromeda has been visible in our sky for as long as there have been human eyes to see it. It will continue to shine long after the last human eye has closed. But right now, tonight, you can step outside and see it for yourself. You can be part of this tradition of wonder. You can connect, if only for a moment, with 1 trillion distant suns and the vast dark matter ocean that surrounds them. That connection, that moment of cosmic awareness, is available to anyone who takes the time to look up. It costs nothing. It requires no special equipment. It asks only that you find a dark sky and an open heart. The universe is there waiting to be seen. Andromeda is there waiting to be understood. The true scale is there waiting to transform your perspective. Go outside, look up, see what waits for you among the stars. The night sky holds countless wonders, but few match the Andromeda Galaxy for sheer scale and significance. From its trillion stars to its invisible dark matter halo, from its approach velocity to its future as part of Milky Way, every aspect of this galaxy challenges us to expand our thinking beyond the familiar. The universe has given us a neighbor, a laboratory, and a destiny all wrapped into one elegant spiral stretching across 220,000 light years. When you find that faint fuzzy glow in the autumn sky, remember that you are seeing the light of 1 trillion suns, reaching out across the cosmic void to touch your eyes and awaken your wonder.